here is what we are going to be doing today. Yesterday, we learned about energy. We went through different types of energy. We talked about potential energy, which is energy that is stored. We talked about lots of different subtypes of that, how you can store energy in food or fuel, and when we do that, we call it chemical potential energy. How you could store energy by lifting an object up high, and if you did that, we call it gravitational potential energy. How you could store energy by stretching or bending an object out of shape, and if we do that, we call it elastic potential energy. Or how we can store energy in things like batteries, and that gives us electrical potential energy. We talked about the energy of motion, which is kinetic energy. We talked about electricity and how to generate electricity using things like turbines. So remember, we talked our way through how different power plants worked, how you could have something like a stream of wind, which is kinetic energy, and that kinetic energy spins the wind turbine. Again, kinetic energy, because it's an object moving. And then at the core of that turbine, there's a bunch of magnets spinning around a wire. And when you spin magnets around a wire, it creates a flow of electricity. We talked about how a lot of the different types of power plants rely on boiling water and then using that steam to spin a turbine. So whether you're burning coal or oil or natural gas, or whether you're just getting heat from nuclear fission, all of those just generate heat, use the heat to boil water, the steam floats upwards, spins a turbine, and we use that turbine that's got magnets at the core, spinning magnets around a wire, generates an electrical current, now we got electricity. We talked about how all of these different forms of energy you can trace back to the sun and the nuclear fusion that's happening in the sun, with a handful of exceptions. Right? If you have geothermal energy that's coming from the heat of the Earth's core that's been there since our planet formed, and if you have nuclear energy, then it's coming directly from the destruction of matter, right? We talked about the law of conservation of energy yesterday, which says that energy can never be created or destroyed, it only changes form. We talked about the one exception to that, which is nuclear energy. So that's where we are currently. Right? We talked about all of that yesterday, and now we're moving into talking about work. So, work and energy are kind of two sides of the same coin. Work is just a word we use to talk about ways of transferring energy from one thing to another. It's really, really important to remember that in this classroom, we're using like a particular dialect of physics English, and the words don't necessarily mean the same thing that they do in regular English. In regular English, if I exhaust myself, I've done a bunch of work. But I could come into this classroom at dawn, and I could, throw all of my might and all of my force and push as hard as I could against that concrete wall, and I can do that from dawn till dusk or until I collapse from exhaustion. And if I don't actually move that wall, I have done zero work. Because work in physics has a really specific definition. In physics, work is a way of transferring energy from one object to another by applying a force to move an object a distance. So there has to be both a force and a distance that we apply that force over in order for it to do any work. We gave you this formula for work. Work is force multiplied by distance. So W equals F times D. This does not mean that if you're doing more work, that you are trying harder. Work does not mean effort. Work does not mean how difficult something is. If you apply a very gentle force, but you do so for a really long time, you could do a lot of work, and it might not be very hard. If you push really, really hard, if you apply a big force, but you only do it for a really small distance, that might be very difficult. It might be hard, it might be effortful. But you might not accomplish much work. So even though in English work refers to like things that are difficult, that's not what it means in physics, and it's really important to remember that. So to start, one of the things I want you to do is I want you to look correlations, things where two things increase together. We've been talking about inverse correlations, things where as one thing increases, the other one decreases. I'm going to give you about a minute to discuss with your table crew. Are force and distance directly correlated, or are they inversely correlated? So go ahead and discuss. All right, I would like you to refocus your attention forward, so bring that conversation to a close. Oh, that was beautifully done. Thank you. Nice. All right, raise your hand if you think you can explain to the class. Is the correlation between force and distance direct or inverse, and why? A.
I think it's inverse.
Why?
Because I don't think it matters how much force you're pushing, like what the distance is for how much force.
All right, so you think inverse, that would mean that if we have more force, we can do the same amount of work with less distance. And if we have less force, we have to do more distance in order to get the same amount of work. Yes, this makes sense. And we can think about this mathematically. Like, let's say I had 20, I haven't told you about the units of work yet, but let's say I have 20 joules of work. Right? I could get that 20 joules of work with 20 newtons of force and 1 meter of distance. Or I could get it with 1 newton of force and 20 meters of distance. And either way, I get to the same answer. So this is an inverse correlation. When you think about how hard or how difficult something is, you're really thinking about how much force it takes. So remember that work is not how hard it is. Force is how hard it is. That's how difficult it is to do something. You can get a lot of work done without using a big force. Yes, Desmond?
What does the J stand for?
All right, let's talk about that. What does the J stand for? Let's talk about units. At the very beginning of the year, we talked about velocity. And we talked about how velocity was distance divided by time. So we had meters and seconds. Meters divided by seconds gets us meters per second. Then we talked about acceleration. We talked about how acceleration was the change in velocity divided by time. So we had to take our meters per second, divide by seconds again, we got meters per second per second. Then we talked about force. And force was mass multiplied by acceleration. So we had to take our mass unit, kilograms, and multiply by our acceleration unit, meters per second per second. So the force here is measured in newtons. But remember what a newton really is a newton is a kilogram, the mass unit, multiplied by a meter per second, which is our acceleration unit. I see your hand, I'll get you another. Oh, you need some help. Now, distance we measure in meters. So really, our formula here is that the unit for work is a newton times a meter, which is a kilogram multiplied by meters, divided by seconds again. This is a nightmare of a unit. And nobody wants to talk about kilogram meters squared per second squared. So we gave it a name. And the name we gave it is a joule. We use a capital J to stand for it. It's spelled Joules. It's named after some guy. So this is our unit for work. Because work is a transfer of energy, joule is not just our unit for work, it's also our unit for energy. All right. So, a thing I want to make sure we take the time to do, in your notes, you should have this physics formulas page, which has velocity is distance over time, acceleration is change in velocity over time, F equals ma. I want you to add this new formula to it. The work equals force times distance. Please make sure that that is added to your physics formula page. What I want to do next is so I've said this thing about, oh, hey, these things are inversely correlated. I want to help cement that knowledge in your mind by making you actually feel it, okay? So we're going to take a really simple action. We're going to open a door. Opening a door takes a certain amount of work. When you open a door, you are giving that door energy. You're transferring energy from you to the door as you push it open. You apply a force to the door, and you move that door a distance. Feel good? So you apply a force to the door, and you move that door a distance. Now, if imagine this is the hinge of the door. This is the door. If I push from here, right, like a normal person opening a normal door, the door moves a pretty big distance, right? Think about how far my hand moves. It goes from here to here. It's a bigger distance, okay? If I push in close to the hinges, like my finger's here, notice how little my finger actually moves when I do this? See how much of a smaller distance that is? So if I push in close to the hinges, if the distance goes down, what's going to happen to the force?
Force goes up.
Yeah, force goes up. So what I'm going to make you do is stand there like very silly people, push it on the door for a bit. Max, this might require slightly more active filmography for a moment.
Get me in it.
But what you are going to do is y'all are going to come over here. You know what it feels like to open a door normally, where you move a bigger distance, but it doesn't take much force. I'm going to ask you to come and push in close to the hinges. Try to keep yourself within about 10 centimeters of the hinges. And if you push from here, you will see, hey, my hands don't move very far, but it's a big force. All right. So the key idea I want you to take from this is that work is not the same thing as effort. Effort is how hard you push. So you pushed really hard in close to the hinges, but you did the same amount of work as you do every time you open the door. It's just that normally opening the door, the distance is big and the force is small. This way of opening the door, the distance is small. Your hands barely moved, but the force was big. Both techniques took the same amount of work. In both cases, you're transferring the same amount of energy to the door. This is really important because this is basically what we're doing in the Mousetrap Car project. If you imagine a mousetrap, what a mousetrap is, it's just a little thing here, and it's got there's a part of the mousetrap called a kill bar. It's exactly what it sounds like. There's this little bar on a spring, and we bend it out of place. As we bend it out of place, we're doing work on that spring. And what it can do is it slams down a really short distance with a really big amount of force. It's enough force to snap a mouse's neck, right? That's the amount of force a mousetrap is going to do. Don't worry, you're not going to kill any mice during this project. So that's what a mousetrap is designed to do. What we're going to do is we're going to use that same amount of energy. There's elastic potential energy that's stored in that spring. And we're going to use that elastic potential energy to do the same amount of work that it would do if it was killing a mouse. But instead of having it apply a big force over a short distance, we wanted to apply a tiny force over a really big distance. Because your goal in this project is to make this car travel as far as possible. So we're going to go a big distance with your mousetrap cars. But you don't need much force, right? You just need enough force to make this car accelerate even a little bit. Now, with that said, everyone has the same well of energy to work with. All of you have one mousetrap spring and nothing more to make your car go. So the big difference here is not how much energy you have, but rather how efficiently you can use this energy. Because we remember that law of conservation of energy. Energy is never created or destroyed. It only changes form. You are trying to turn this, this elastic potential energy into kinetic energy. But there's other things it could turn into. Friction will turn kinetic energy into heat. If you rub your hands together, you can feel them get hot, right? Kinetic energy turns into heat when you do that. Yeah. Right? So that's what friction does. That's how friction slows things down, is it takes the energy in the form of heat. Yeah?
Does that mean heat equals kinetic energy times heat?
It means that however much total energy you've got a certain amount of total energy, and it can turn into different things. You want it to all turn into kinetic energy. But instead, some of it's going to turn into heat. Some of it will probably turn into sound. If your car makes noise when it's traveling, that means that some of the energy is turning into sound. Right? So if there's any grinding happening in your car, that's a bad thing. It means your energy is not being transformed efficiently. So your job is to make this energy transfer as efficient as possible. Now the biggest inefficiency that you're going to face is going to be friction. So figuring out how to remove as much friction as possible, that's going to be huge for your mousetrap cars. That's typically what makes a mousetrap car live or die, is how much friction is there. We good? Okay. The other big thing that's going to make a difference is stuff like air resistance. Air resistance is proportional to velocity. The faster this thing goes, the more air resistance it's going to be up against. So you actually don't want your car to go fast. You want your car to move slow and steady, because the faster it's going, the more air resistance there's going to be. So you can actually reduce air resistance, reduce how much energy is going into moving air out of the way instead of making your car go forward, by simply having it creep forward at a nice, slow, steady pace. So all of the design choices you're going to be making in this are going to be geared towards things like, hey, how do I keep this from wasting energy? How do I make sure my energy transfer is as efficient as possible? And those are the main goals you have here. So you're trying to make sure that this elastic potential energy turns as much as possible into kinetic energy, but that it does so in a way that is minimizing friction, that's minimizing air resistance, that's reducing the amount of energy that's wasting in things like sound. Your job is to make this as efficient a use of energy as possible. That's what we are aiming for in our mousetrap cars.